Okay, so there's three major takeaways from what we're interested in chapter 15. Okay, and the first area we're going to look at is testing the population proportion. Now, we've done proportions before in this class as well as business stats. So you're familiar with that word as it relates to some percentage of the whole, right? A proportion, some percentage, which is part of the population or sample. So a sample proportion denoted as P, okay, which is found by X over N. X is the number of observations, right? Number of people who like the color blue, and N is the total number of observations, so total number of people. So if 10 people like the color blue and there's 100 people, then of course 10% is the proportion or the percentage indicating the part of the population or sample liking the color blue. Okay, so we have a P, lowercase p, very important, a symbol there for us. And then we want to compare that later to pi. Okay, and here's pi. And what does it say pi means?
Population proportion.
Population proportion. Okay, so now we're distinguishing between a sample proportion, xn, right, and a population proportion. And as you know, population means that we have the entire group, right, the entire group. And so there is something distinguishing of the entire group. Whereas with P, we have the sample size, right, some piece of the entire group. And then we have some distinguishing feature of the piece of the entire group. So if we say there's 1,000 people in the population, and some percent of them, of course, like the color blue, that would be your pi. And if we say we have 100 people in the sample, and some percent of that 100 like the color blue, that will be your P. Okay, so testing the population proportion. Take a random sample that follows the binomial. If you go back to earlier chapters of the book, I believe it's around 7 or 8, you will see, you'll be reminded of, chapter 6, you'll be reminded of the binomial. So real quick review, there's some characteristics, and here are the 4 of them. They're nominal. The outcome of each observation is a success or failure. And that's in quotes, because if we say, like the color blue is a success, not liking blue is a failure, that's what we mean. It's a binary trait that the outcomes share. The probability of a success is the same, right? Choosing someone as part of the population. If I choose person number 43 and then I go on to choose person number 44, the probability of getting somebody who likes the color blue is the same, right? If I choose person 94 or 97, the probability of that person liking the color blue is the same. So the probability of a success, somebody liking the color blue, is the same for each observed value. Okay. The observations are independent. So choosing one person has no impact on choosing, or choosing a person has not been impacted by a person I chose previously. So it's not as if because I chose 40 people, that 41st person is going to have some sort of different outcome. It doesn't matter. So the binomial distribution has those traits, and those traits are brought into this portion of our testing, which is, again, the population proportion. Okay, so n times pi, right? N times pi, or n times 1 minus pi. If that answer is at least 5, we can use the normal distribution as an approximation to the binomial. Okay, so we'll use z to approximate the binomial. As you know, z is our normal distribution to approximate the binomial. So we take our sample size times our population proportion, and if that number is greater than 5, we can say, yes, there is normality. Remember, if you go back to the whole normality discussion, a lot of it has to do with, well, how much data do you have, right? And whether or not we're going to treat that data as normal has something to do with the number of data points we have. The more data you have, the closer to normality your distribution of that data is. Okay, and so this plays into that from a proportion perspective. because we're saying, hey, what's the size of the sample that we have? And then what's the population proportion? And the bigger this n is, and the bigger this pi is, then the bigger the overall number is going to be. And if it's bigger than 5, right, we're going to treat the data set as normal. Okay, so there's a little test there to get us to normality. Okay, so always the best way to learn stats is with an example. So suppose prior elections in a state. Somebody finish reading that for us.
Indicates it's necessary for a candidate for governor to receive at least 80% of the vote in the northern section of the state to be elected. The incumbent governor is interested in assessing his chances of returning to office and plans to conduct a survey of 2,000 registered voters in the northern section of the state using a hypothesis testing procedure assess the governor's chances of re-election.
Okay, thank you. So tell us what's going on. What's happening here? What's our situation?
Governor who is running for re-election, and he's looking to see what's the chance of him getting re-elected.
Okay. And what parameters are in play? What needs to be in the case, and what is actually the case so far?
He needs to get at least 80% of the voters.
Okay. In what area?
In the northern section.
Okay, so 80% is what's needed, because historically, when a governor receives 80% of the vote in the northern section, that means their chances of winning go way up. Okay, in fact, the word necessary is what we see here, so it's almost a critical need. So the governor is interested in assessing the chances and is going to conduct a survey of 2,000 registered voters. And in what part of the state again?
The northern.
Okay. Of those 2,000, how many need to want to vote for this governor? Of the 2,000, how many need or how many need to say, yes, I'm going to vote for you?
1,600.
1,600. How'd you get to that?
You multiply it.
Okay. You multiply that 80% times the 2,000 and to get the 1,600. Okay. So that's where we are. All right. So state the null hypothesis and the alternate hypothesis. And in this case, we're saying because we have the word at least, remember the word at least means equal to or greater than or equal to. If I say to you, tomorrow I'm going to give you at least $10. That means what?
It's going to be $10 or more.
Exactly. Tomorrow you definitely will receive 10, or you could receive more, but certainly not less. So what does greater than equal to look like? There we go. Greater than or equal to. And that decision to reject the null infers that the governor will not be reelected. So the null hypothesis is I need 80%. Right? That's what remember, the null hypothesis is what has actually happened. It's history. And history says you need 80% of the vote, and our population proportion needs to be 80%. Okay? And of course, the opposite of that is what we call an alternate hypothesis, and it will be less than 0.80 or 80%. So select the level of significance. Let's choose an alpha of 0.05. And then select the test statistic. We're going to use the Z because we've met the assumptions, right? We see an N of, what's our N? What's 2,000. Our N? Okay, and then what's our pi? Pi is equal to what? Yep, pi says right here, pi is equal to 0.8. Okay, it says greater than or equal to, but the equal to means pi is 0.8. Okay, So that 1600 is greater than or equal to 5. So we're going to go ahead and use the normal distribution in this case. Okay, we're going to use the z. Okay, and then if you did the n times 1 minus pi, so 0.2, you'd still be greater than 5. So that's where we get the ability to use the z distribution. All right, so calculating the z-test statistic is right here. But before we do that, let's stay with our let's go with our looking at the critical side first. So this is a one-tailed test, yes or no?
Yes.
Okay, how do you know?
Because it's not equal. It doesn't have equal signs.
Right.
And it gives a direct in the question.
Okay, yeah, that's the better answer because technically there is an equal, right? There, in fact, technically there's always an equal sign,
Right.
meaning right here, right? That's an equal sign. This happens to be also a greater than and less than question. So the best answer is when there is a greater than or less than question, then we're talking about a two-tailed test. When we have only equality, meaning it's equal to or it's not equal to, then we're talking about two tails. So we know we're dealing with a one-tailed test, and we know that we can look in our Z table back at the book or online, or we can just jump into Excel, type in equals, what you got? Equals what? Let's see, equals what?
1.64. Oh, is it f.nv?
F.nv, no, that's our F test. We are looking for Z. What's our Z function?
This is just INVT.
No, we need something before the INV. Remember this?
Oh, yeah. Dang.
Okay, so norm, what you got? What should we use?
Norm.s.inv.
Okay, let's give that a try. What's the probability?
0.05.
Okay, are we splitting it in half?
No.
No, because it's a one-tailed test.
There it is. All right. So our answer here is negative 1.645 if we go 3 decimals. Okay, 1.645. And so that gives us the, I'm just going to move this over. Okay, that gives us the critical Z that we need, of course, negative 1.645. Now, if we look at our alternate, we see what side we're going to be working on, and that's going to be the left side, right? Because we are less than 0, okay? Or I should say we are on the left side. In this case, we're not less than 0, we're at 0.8, but it is telling us that we are on the left side because the alternate is less than, okay? So that's our clue for being on the left side. Okay, so any questions on finding that critical?
No, sir.
All right. Everything else here, and again, I just can't emphasize enough, it's always good to draw this. Always good to draw a normal curve because then you always get a reminder of how this thing works. What's here and what's here, what's on the outside, the rejection region, all of that. Okay, so now we need a now we need a computed Z. And that's the new part of this. We need a formula for the computed Z, and here it is. Sample proportion minus the hypothesized population proportion. Okay, let's look at that first. Let's see what our math looks like. So here is our sample proportion, right? Remember that is our P, okay? And with our P, what is being said? Well, we know what 2,000 is. That's the number of people in the sample. 1,550, though, must be what?
The amount he needs to, well, that must be the 1,600.
Because it doesn't say 1,550 here.
Yes.
So what can we assume that is? If we know what P means.
Is that the amount
The amount that what?
that he needs to get?
Well, the word needs is the issue there. It's not what he needs, it's what he's
What he's gonna get.
well, but
Or
it's
expected to get.
well, remember, right, we're talking about, let me go back to this slide. We're talking about nope. Yes. We're talking about x over n. Okay? So the n is 2000, the x is 1550. The x represents the number of observations with a particular trait. What trait do you think that is of these 2000 people?
The
What's
The
the
ones
trait?
that voted for.
Well, the vote hasn't happened. This is a pre-test, right? We're trying to get a sense of how they're going to vote. So what do you think X means?
Mhm.
Right, 2,000 people, 1550 share a particular trait. What's that trait?
That they will vote that way.
No vote.
Exactly. Yeah, that they will vote for this governor. Okay, that they will vote for this governor. So it's not, so just as a quick correction, right? It's not how much he needs, it's how much people think. It's what people are saying that they will do. Now we know what he needs. What does he need?
He need the 1,600.
Right, right. But he's actually, based on this preliminary poll, right? Remember, let's look at our language again, right? Suppose prior elections in a certain state necessary for this to happen. The governor is interested in assessing chances of returning to office and conducts a survey. So this is not a vote. This is a survey of 2,000 voters. And of these 2,000, 1,550 say, I'm going to vote for you. Okay. And so the question is this P, right? This percentage, what do we call it? This sample proportion, is that significant? Is that significantly different than 0.8? Okay. That's really what we're doing now. We're asking if this P is significantly different than 0.8. Because if it is, then that's not a good thing, because it's not close enough to 0.8. Okay. If it isn't, if there's no difference between 0.775, which is what it breaks down to, if there's no difference between this number and that number, then the governor can feel good about his chances in the northern part of the state, because statistically there is no difference, right? So we are testing effectively if there's a difference between these two numbers. Okay, so that's our numerator. Our denominator, pretty easy math. We just take, right, our pi times 1 minus pi, so 0.2 over the n, and we have this as our square root, and ultimately that gives us the negative 2.8. So again, just a refresher, we're looking at how the actual survey data, 1,550 over 2,000, is compared to what you need, 0.8, right? The hypothesized population proportion. If there is a significant difference between the two, not a good thing if this P is less than what you need. Now, if the P is 0.9, right, we tested, we come to some conclusions and we take some other roads. But because it's less, we have to figure out if they are different. Okay? So that's why we're doing this, to see if there is a difference between a statistically significant difference between P and pi. Mathematically, we can see there's a difference. 0.775 is different than 0.8. But as I always say, the surface is not enough. We have to look deeper and see if there is a significant difference statistically between these two numbers. And so we run this test. We see that negative 2.8, does it fall in the rejection region?
Yes.
It does, right? It's going to fall somewhere in the rejection region because it's less than negative 1.6, okay? So what in the world are we rejecting?
That,
What are we rejecting? just normally when we reject something, what do we reject?
Well, rejecting the null.
Okay. We're rejecting the fact that a proportion is greater than or equal to 0.8. But this interpretation is a little bit different. Okay, this interpretation is a little bit different because yeah, we can say our pi is greater than or equal to 0.8, but that doesn't really help us understand what we're trying to conclude. What we're trying to conclude is there a statistical difference between these two numbers? So here's the better language. The difference of 2.5. Now, where do we get 2.5? Well, if we took 77, if we move the decimal over, made this an actual percentage, we take the decimal, move it over 2 places, and we get 77.5. And making 0.8 a percentage, we would get 80. So the difference between 77.5 and 80 is 2.5. So the 2.5 percentage points between the sample and the population proportion is stat sig, is statistically significant. Okay. Now, we can say that because we have rejected this fact, right? We've rejected the null hypothesis, so we can therefore conclude that there is a difference. Therefore, the evidence at this point does not support the claim that the incumbent governor will return to the governor's mansion for another 4 years. Because we have rejected, again, we have rejected the fact that the population proportion is greater than 0.8. The population proportion we received of 0.775 is not greater, or I should say the sample proportion we received of 775 is not greater than 0.8. Okay, so when you are looking at least population proportions, we are comparing a p to a pi and asking ourselves, is there a difference between these numbers? A statistically significant difference. Again, obviously they are different. 0.775 is different than 0.8. But is there a statistically significant difference? In this case, yes. Okay. And if it is true that 0.775 is not very close, is not statistically close to 0.8, then 0.775 will not get you enough votes. Okay. It's not close enough to 0.8 to say that you can win this thing. So that's the difference between kind of what we've done before and what we're doing now. Any questions on that?
I got it.
All right. We lost Dolly. And Nikisha, you got it?
Yeah, she sent a message.
Oh, really? Oh, she was offline?
Yeah, she had to go.
Oh, Dolly had to go?
Yeah.
Oh,
Yeah,
okay.
I'm still here.
Nikisha, okay, still got you. All right, good. Any questions, Nikisha?
No, sir.
Okay. All right, let's go to the second portion of this. There's 3 main points I want to cover today. So this is number 2. Okay, so that first one gave us a 1 sample test, 1550 over the 2000 was, you took a sample and this was the trait that they shared. But in this case, we're going to look at 2 samples. When we look at those 2 samples, we're going to have another z, computed z, that we're going to need to compare to a critical z. And so this is going to be our new computed z right here. Now the p, the logic of the p stays the same. It's the proportion in the sample possessing the trait. Now it says sub 1 or p1, and so now we're saying the first sample. And of course, p2 is the second sample. And our new addition is PC, which is the pooled proportion, which basically means what's the proportion of both samples, right? We're basically combining the samples to come up with one, what we call pooled proportion. When you're pooling something, you're usually combining 2 variables, 2 elements, 2 samples, okay? And so that's what the PC means. And we have to have a PC because if we're looking at a 2 sample test, we have to have a way to combine the 2 samples into one logical P in order to do the statistical analysis. And so combining those two samples into 1P, that 1P is called the PC. Okay, the pooled proportion. All right. And then we're going to have estimating the population proportion. We will get into this as well. So there's kind of the PC that is right here. The math for it is right here. Okay. So again, let me just reiterate. This is a computed Z formula. This is our new one, computed Z. In order to get the computed Z, though, we have to have PC, and that's our simple math for PC. All right. You have a perfume company. Somebody read that to us. Let's go with Javon this time.
All right. Manelli Perfume Company recently developed a new fragrance that it plans to market under the name Heavenly. A number of market studies indicate that Heavenly has a very good market potential. The sales department of Manelli is particularly interested in whether there is a difference in the proportions of younger and older women who purchase Heavenly if it were marketed. Samples are collected from each of these independent groups. Each woman is asked to smell Heavenly and indicate whether she would purchase the fragrance.
Okay, so we can see what's in play here, right? There's a new product, and if you're a marketing major or even management, right? This is everyday. This is critical stuff. So you got a new product. Do people like it? And if they do like it, what kind of people like it? And before you can put it on the shelves, you might want to know who you want to spend your marketing dollars on. Marketing has a lot of stats involved with it because you want to know human behavior. And really, one of the best ways to assess human behavior is just run a survey out there, right? Arguably the best way, just ask people what they would do. And so you're asking younger and older women if they like it. Okay, so that's the bottom line here. And then look at this language in stats. We look for some coded language here. Is there a difference? Right? That tells me we're not looking for greater than or less than. We're looking for what?
If they're equal to or not equal to.
There you go. There you go. It didn't say are there more younger women or less younger. It's saying is there a difference? So hypothesis testing, that's a big code piece of language because it's going to take us to the two-tailed test. All right. So when we look at this, we are saying number one, here is that they are equal. Okay. We have proportions that are equal, and then we have not equal. Okay, so that's our null, and that's our alternate, as we already said. We're going with a 0.05, and we're going to use the Z because here we're assuming the sample sizes will be relatively large. Now, they have not given us sample sizes, right? They did not say here's our N, here's our N1, here's our N2, but in this case, they just said it's going to be big enough, go ahead and use the Z. So I understand if that's a little confusing because technically, right, we don't have any ends, right, to say anything's greater than or equal to 5. But they just kind of zoomed us right into the fact that we're going to use it. So just FYI on that one. We know there's going to be a splitting of the alpha because we have a two-tailed test. So if we run the norm SINV, what is changing here?
We're gonna divide the significant.
Right, we're going to divide the alpha, and when we divide that alpha, we're going to get a 1.96. Okay, so that's where we get our 1.96. As you know, that's going to be two-tailed, so it's going to be on both sides. And if our computed Z falls into the rejection region, we know we are rejecting the null hypothesis. Okay. All right, so step 5, we do a little bit of math here. Select the sample, do the analysis, make a decision. So P1, let's go with younger women. Okay, that's going to be P1. Now, of the younger women, how many were asked? And here's our answer in here. What's the sample size of the younger women?
100.
Okay. How many of them like the perfume?
19.
19, there you go. So going back here, who would purchase Heavenly if it were marketed? Okay, that's what we're saying. So our test was who would purchase Heavenly if it were marketed. And in our null and alternate hypothesis, right, we were asked, if we look back here at what our P and our pi's mean, population proportion is equal, population proportion is not equal. Okay. All right. So in terms of our sample here, we have N of 100, 19 would buy it, assuming because they like it. With our N here, we have 200 and 62 of the 200 older women were asked, and 62 of them said, hey, I would buy it. Okay. So on the surface, which group of women like it more?
The older women.
Right, because their percentage is higher. So on the surface, we could stop there and say, well, let's market to older women, right? But the reason you're learning stats is to get a deeper analysis of this difference, right? You're not only interested in, 31% compared to 19. No, you want to know if they are statistically the same or statistically different. Because if they are statistically the same, then you shouldn't target older women, okay? All right, so now let's construct that PC. Very simple, 19 plus 62, 100 plus 200, and the end is 0.27, so that's our PC. And let's drop that PC right here, and then take 1 minus on both sides, and then we put our N, and then we're going to compare the 19 to the 31, okay? So this is our computed Z. Our computed Z gives us a number of negative 2.207. Okay, everybody sees how we got that number.
Mm-hmm.
Okay. Mm-hmm. Always test this yourself. Okay. Always go in and test these yourself. Create a model in Excel where you can easily drop the numbers in and get your computed Z. That will help you a lot when you're taking tests or doing homework, because you don't have to sit there and recreate this whole structure. If you go in, and what I'm saying is, if in Excel you do this, right? P1, P2, PC, and N1, N2, and if you do this, and then you create a system where all you got to do is change the number for each of these, and then your final answer, right? Computed Z, out pops your computed Z every time that you change these numbers. That's a whole lot faster than having to do it individually.
Yeah, that's what I did. That's for the last test, but I left my computer at home.
Oh, Lord. Okay.
Yeah, when I went to the test.
Where'd you take the test?
I had to take it to the library because my computer wasn't connecting to my Wi-Fi at home, so I had to go to the library.
Oh, well, on campus?
Yeah, on campus.
Okay. Okay, so let me understand this. You had it on your home. Oh, okay. So it wasn't in like the cloud. It wasn't in Dropbox, iCloud, or something.
It was just on a page on my.
Oh, on your hard drive.
Yeah.
Man, you're talking to one of the biggest advocates of using the cloud, so that concerns me. But yeah, going forward, use the free cloud, whether it's Google Docs or Dropbox, iCloud, whatever. It's so worth it, because something like that could save you time. I looked at the grades. I think you did pretty well. I don't remember specifically, but how did you do? You tell me. Don't tell me the number, of course. Just how do you feel you did?
No, I didn't do too well as well as I thought I would.
Oh, really? Okay, I might have you mistaken with somebody else. Okay. Yeah, the grades were very dispersed. So, yeah, man. For everybody listening, please use the cloud so that you can access it from anywhere on
I
Earth.
don't know anything about the cloud. I'm like an old head. I don't know.
That's the thing. I pay for the cloud too.
Oh, Lord. Okay. Which one do you pay for?
I got the Apple Cloud, the iCloud.
The iCloud. Okay. Yeah. If you have an iPhone, you're probably paying at least $1 a month for those 50 gigs. Nikisha, all we're saying, the cloud is just a fancy word to say use. You have an iPhone?
Yeah, I have one of those.
Okay. So you've seen iCloud somewhere as you've been using your iPhone.
Yeah, but I never connected it to it. Okay. Like I don't know how to whatever you're supposed to do. I don't know how to do it.
Okay, okay. Just FYI, yeah, this fall we're actually doing some trainings on how to use the cloud for these types of things. So just kind of look around campus. I'll be posting it on the walls and whatnot on how to use the cloud. But just all I'm saying is if you probably have an Apple ID, so to use your phone, you have to have an Apple ID to do anything
Yeah,
with
I do.
iTunes. Okay. So go to iCloud.com and type in your Apple ID when you get a chance, and you'll see you'll see your calendar, you'll see your email, and you'll also see they don't call it documents. I think I forget what they call it, but it might files or documents or something like that. And that's where your items are saved that you have purposefully saved to the cloud. So again, iCloud.com, type in your Apple ID and you'll see all of your cloud items. Now, if you are saying Word and you don't on purpose save stuff to your iCloud account, it won't be there. So go to YouTube and just type using iCloud and you'll see a million videos on how to do this. Okay, and it'll save you a bunch of hassle. Uh-huh. Go ahead,
I was
Javon.
gonna say if you have like a MacBook or anything, if you save it, just save it to your desktop, it'll automatically cloud like that.
Ah, there you go. There you go.
Yeah. Oh, and I had a question on actually this one because I was setting it up and I have it all set up in my Excel, but I keep coming out with the wrong D every time I calculate it in Excel.
Ah, okay. So you're working on this one?
No, I'm on actually on the practice for 15 on Connect.
Okay.
One of the
But it is it this computed Z question?
Yeah, it's the two-tail for Computer Z.
Okay, so it's this one here, P1 minus P2.
Yeah.
Okay. So the best advice I can give here is to take it in steps. A lot of times people try to knock out that whole formula in one step, and that would be a mistake. Let me do this. Let me real quick pull this over so we can have it all on one screen. Okay. All right. So the way I would approach this is, okay, so let's first make sure we have everything. There's my P1, there's my P2, there's my PC, and there's my N1 and 2. So I have all the variables I need. So in fact, I would take this, and if I'm doing this for real, I'm going to bring this down here. So we're going to be some intermediate steps. So here is my P1 minus P2. And what I'm going to do is put equals, right? I'm going to take that number minus that number. Okay, and then whatever I drop in here going forward, right, will always be correct. Okay, and actually let me drop.
Okay.
Okay, so let me put the actual numbers in. Okay, and then so let's look at the bottom here. This is a little complicated, so we're going to do this in steps. So let me take the numerator here first. PC times 1 minus PC, and I'm going to put that here. PC times 1 minus PC. Okay. And so I'm going to do equals, and I'm going to take PC, which is F13, times 1 minus the same thing, F13, close parentheses. Okay. So whenever I put a PC in there, and the PC in this case is 0.27, right, I'll get, why am I not getting that? Let me see. PC, it's saying it's circular.
I don't think it had a number in there.
In where? Did I put equals?
When you first did it, I don't think, when you put the PC in there the first time, I don't think it had a number in there.
You got to put a multiplication between the F13
oh,
and the
okay, okay. Thank you. Yeah, the mac's a little bit different in that regard. Yeah. Okay. Thank you. Okay, and then we have N1. So I'm going to take this whole thing, and actually, you know what? Let me just do this, and I'm going to put divided by N1. Okay, so now I'm going to take equals minus that number divided by N1, which is F14. And N1 in this case is 100. Nope, changed the wrong thing. N100. There we go. Okay, so now I have the left side of the equation, and actually the right side is the same numerator right here, but now it's over n2. So I'm going to copy that and put n2 there, and so that equals this divided by that. Okay, and that's going to give me 200. Okay, now the last step, well, second to last, let me make this, move this down here. We got to get that new, we got to add those two together. Okay, so I'm not, I should write this plus that. That will be this next one right here, this plus that. So let me just do that right here, just for speed's sake. So this plus that gives me this.
Mm-hmm.
And now I need the square root of that. Okay, so equals square root of this. Okay, so that's my denominator. Okay, we can call that the denominator. Okay, and we have our numerator right here. Okay, and so we're going to do equals numerator divided by denominator. Okay, and there's our 2.207, and I'll move these over. Okay, so if you didn't get it, all that means is somewhere in the steps, somewhere in the step process, things got confused. So
Yeah, I tried to take it out in all one formula. That's where I probably messed up.
yeah, it gets a little too heavy. See, I even made a mistake just trying to do it with that little piece. So if you try to do it with this whole thing, it gets a little messy. But the beauty of having this, as you know, right, the whole beauty of having this now is that every time something changes, you don't have to worry about doing the math. You just change this area right here.
Mm-hmm.
Okay, so if you get a new problem and it's 0.07 and this is 0.29 and this is 0.56 and this turns into 150 and that turns into 175, you're done, right? You got a computed Z. Okay, so make sure we have those models built. Okay, so what we're concluding here is that negative 2.207 is our computed value, keeping in mind that our critical was what? What was our critical? Critical Z. Oops. Critical Z.
Was it negative 2 point something?
No, our computed was. But what did we see right here? What's our critical Z?
1.96.
Negative 1.96.
Right. Our critical Z is negative 1.96 and 1.96. Okay. Remember, the critical Z establishes our area of rejection. Okay, it establishes the beginning of the region or the area of rejection. So what's the beginning of the region of rejection here? Negative 196. What is it over here? Positive 196. Okay, so we want to compare that 196, negative 196 to this number. So what do we conclude? Is this number less than negative 196?
Yes.
It is. Therefore, it is to the left of this negative 196, which puts it in the rejection region. Therefore, we are rejecting this fact. Okay, we are rejecting this fact. And so the interpretation, the proportions of young and older women who purchase heavenly are different because the proportions here in our null is that they are the same. We're rejecting this, that the proportions are the same. Right? And so if we're rejecting the null hypothesis, we are not rejecting the alternate, which is that they are indeed different. So by observation, the proportions indicate that older women are more likely to prefer the fragrance because the proportions are different. And if one is higher than the other, we can say statistically that 31% is higher than that 19%. So again, on the surface, obvious. Statistically, though, we got to run some tests. And our hypothesis test says that, in fact, they are different. So yes, we can now, if this is the only thing you do, and it shouldn't be, of course, but if this is all you do to figure out who to sell to, statistically, it's a good decision. But should you take more samples and do this a lot just to confirm it? Of course, if we're in the real world. Okay, questions on that?
No, sir.
Okay. The last thing, and we're going to run over a little bit, but that's okay with me. If it's okay with you, are we good on time?
Yeah, we're good.
Yes.
Okay, it's 12:03. We got some time. All right, so the last thing I want to do, and this is actually the last part of the chapter that we're going to cover for chapter 15. So this is where your, this is where your homework ends. And when we do the test too, this will be as much as we cover in 15. So now we're looking into something a little bit different. We want to look at something called observed and expected frequencies, okay? And we want to know, in terms of the null hypothesis, are these observed and expecteds different or not? Okay, so there is no difference is the null, and there is a difference, as usual, with the alternate. We're having a new distribution. This is called the chi-squared, CHI square, okay? In my training, I just learned it as chi. If you say chai because there's chai tea out there and there's other, I guess, well, there's chi, not chai tea, that's CHAI, isn't it? But there's other things with word chai. I understand that. I don't care so much how you say it, as long as you understand it, but I call it chi. All right, the major characteristics of the chi-squared is it's positive, okay? So we're going to be on the right side. It's non-negative, and the shape depends on its degrees of freedom. So similar to the F in that it's positive, and also similar to the F in that we're looking at degrees of freedom. Also, the T has degrees of freedoms that we look at as well. But we're using the chi-squared specifically because we're looking at observed and expected frequency distributions, okay? So here's what the computed chi-squared will look like, and we'll get to that. No need to introduce this now. Let's take a look at an example. We have Bubba's Fish and Pasta, and they hired Magnolia Research because Magnolia Research does great surveys, and Bubba wants to do what? Add steak to the menu. But first, Bubba says, do people prefer steak? Okay, do people prefer, meat? So, or do people really just strongly prefer, the seafood because they're on the Gulf Coast of Florida? So, hires Magnolia to do some research. Magnolia selects a sample of 120 adults. Okay, these 120 adults give some feedback. Now, before the feedback is given, here's a logical expectation of what Magnolia may think is going to happen. 30 people will like chicken, 30 will like fish, etc. And of course, where does that 30 come from? Where does that 30 come from?
The 120 divided by 4.
There you go. So logically, one could assume that on average, people will like things the same. So that's why we call that expected, because we could expect on average it to be the same. So there you go. Now, after the survey was done, here's the actual distribution. Here's the actual distribution. Instead of 30 people liking chicken, 32. Instead of 30 people liking fish, 24 did. And 30 people, instead of 30 people liking meat received the highest number, 35, which is what Bubba wanted to see, actually, because he wants to add meat to the menu. And pasta, 29. So the expected frequency infers adults have no preference. They're indifferent. Whereas the observed is what actually happened. Now we have to test whether or not this set of numbers is different than this set. So the chi-squared is going to ask the question, is this different than this? Now, on the surface, again, you could stop right here and say, go ahead and offer that meat. Clearly, people expect it. Or no, I'm sorry. Clearly, people prefer it. You could stop right there, and on paper, mathematically, very simply, people want the meat more than others, more than other things. But you see the problem. Oh, hold on. Okay. The problem. How's your sound? Is your sound okay?
Yeah, it's good.
Okay. The problem with that logic, though, is these numbers could be statistically insignificant in comparison to these numbers, right? The difference between this set of data, these two sets of data, could be insignificant. And so you should not make a decision until you run the significance test. All right. So how do we do that? HO, no difference between the two columns of data. H1, there is a difference. Alpha, 0.05. We're going to use the chi-squared. Why? Because we are comparing observed and expected frequency distributions. That's why we're using it. Okay, so the decision rule is going to come from the following. We are going to reject HO if our computed chi-squared is greater than our critical chi-squared. I have some good news for you. The critical chi-squared is very easy to get. A, there is a table in the back of the book for it. And B, there's an Excel function. Okay, so we're looking for 7.185. Where does that come from? It comes from an alpha of 0.05 right there. Okay, and that's the 0.05 right here. And it comes from 3. Now, where do we get 3 from?
The 4 minus 1.
Okay, and what is 4? What's the 4 come from?
The what is it? The 120 divided by
I didn't hear that last part.
It's the 4 options that they have.
Yeah, the 4 categories.
Right. So the K is going to be your number of variables, and there are 4 variables: the chicken, the fish, etc. So 4, just like your T distribution or your F, right? 4 minus 1 gives you 3. So if you look in the table, you will get 7.185, or you could compute this using Excel, and our function here is going to be equals chi-square INV RT. And it's going to ask you first for the probability, which was what? What's our probability?
0.05.
0.05. And then our degrees of freedom?
3.
3. All right, and there's our 7.815. Okay, so very simple. Once you understand that function of chi-square.inv.rt, you're done. And keep in mind too, this is very similar to the F, right? Before we dropped an F in there and we found our F. And again, the RT means we're going to be on that right side, which is one of the rules for this use of the chi-squared. Okay, so there's our 7.815. What do we call that again? What is that called? The 7.1.
It's the critical pi.
It's the critical chi-squared.
Chi.
Yeah, the critical chi-squared. Okay, now we have to compare that to a computed. Earlier, it showed you how to get the computed, which is right here. So let's look at that math. And of course, before I do that, right side, here's 7.815, which is your critical area. Done and done. All right. Now let's do the math here. And there is no Excel function for this, at least not a fast one. You could build one, and you should, in terms of building the model. But to just say equals computed chi-squared is not out there. At least I haven't seen it. Excel changes a lot though, so who knows? Maybe somebody wrote a macro for it. Okay, so FO. Okay, so that's our observed frequency. Remember that column of data from before. FE, remember that column of data. And let's do some simple math and subtract them from each other. There you go. So 32 minus 30 is 2. 24 minus 30 is -6, etc. And let's go ahead and square that. 2 squared is 4. -6 squared is 36. There's our data. And let's take that square number and divide it by the expected frequency. So if we take that 4 over the 30, we're going to get 0.133, etc. Okay, to get that column of data. Let's go ahead and add those up, and that's what this summation symbol here means. Let's add those up, and we get 2.2. So very simple math. And could you create a model for this? Yes, you could, because you would leave these blank, and you would just do the math in here, right? You would create the mathematical operations in here. You know, but the difference, of course, could be you might not have a K of 4 for your next product. You might have a K of 10. But if you build all this, then all you got to do is drag stuff, right? So if you build it with 4 and you get, say, a K of 10 or a K of 8, then all you got to do is drag your last column down, and everything should still work if you pre-build this model. You can pre-build almost anything in Excel. So this is what we call a computed chi-squared, and it's 2.2, much less than the 7.85. And because it does not fall in the rejection region, the decision is to fail to reject HO. We always ask ourselves, what was the HO again? Right? And we go back to the original question. HO was that there's no difference between the expected and the observed. There is no difference, which means these two columns of data are effectively the same. The fact that there are some higher numbers here compared to these should not make you want to make any decisions based on those numbers being higher or even lower. Okay, so interpret the result. The difference between the observed and the expected is due to chance, right? Perhaps you asked people who just, you know, you happen to ask a group of people who lean meat, but if you ask 120 more people, you may get people who don't lean towards meat. They lean towards chicken or fish, or I should say steak. They lean towards chicken or fish instead. Okay, so there appears to be no difference in the preference among the 4 entrees. Okay, so if you're Bubba, what does that lead you to believe?
That you really don't have to change a menu.
Yeah, it means that, you know, adding steak based on this wouldn't be the best decision, right? You should go get another sample, but don't, you know, make a quick decision now because people don't have a higher preference for meat necessarily. Yeah. Okay. But that also, on the positive side, could make you believe what?
That adding it wouldn't hurt.
That they what?
That adding it wouldn't hurt.
Exactly, right? On the other side, people are indifferent because if this set of data is the same as this set of data statistically, that means adding meat won't necessarily be a bad thing either because people will eat it at the same level, will prefer it at the same level they prefer everything else. Mm. So for Bubba, that could be the conclusion that he runs with. Now, if Bubba's goal was to start replacing, see, here's the nuance, to start replacing, let's say, you know, fish with meats, well, that's different because people have no stronger preference statistically for meat. But if the goal is simply to, as it says here, add meat without replacing anything, these results may be fine for Bubba to make that decision. So you can see there's a bit of nuance here when it comes to this particular conclusion. You see that?
Yep.
Okay. We stop here in terms of this chapter. We're not going to get into the unequal. This is still the chi-square, but it's just that now things will be unequal instead of equal in our expected area. So we're not getting into that, not getting into the rest. So make sure you master everything from this slide and before it. Any questions?
No, sir.
Okay, just as a quick wrap up, let's see here. Okay, we had the homework 4 out there, due Friday. Participation 2, that's going to be due Sunday at 5. And participation 2 relates to chapter 17. And that, of course, we already have a video out there for that. So you should be fine with those. as things work out for you, I recommend share information, help folks out if they have questions, because that's always a good thing, because you may be the one needing the help next time and they know it better than you. So working in groups, even though this is online, use Slack as much as you can. And just, hopefully you already are. You're having some conversations about how these things work. Okay, that is it for this session. I'll work on this video and hopefully get it up by the end of day, no later than tomorrow. Okay.
Yeah. Oh,
yep.
Did you say anything about extra credit or anything like that? Have any of that?
Typically, I do throw some 1 or 2 points out there. So if I do it, it would be, let me see, today is Tuesday. So it would probably be late this week, maybe Monday at the latest, because you would need a few days. I believe I've done it for online before. So you'll probably get some of that. It's not a ton, so that's not, it's not a game-changing amount. But it could, it helps. It helps a little bit. Okay. Hello?
Yeah. Thank you.
No problem. Any other questions?
No, sir.
That's it.
All righty. We will talk again later. Stay on Slack, or shoot me an email if you have any questions.
Yes, sir.
All right. Bye.
All right. Bye.